Okay, for this second lesson with systems, we're going to look at determining the number of solutions to a specific set of linear equations. So for the exploration, we're looking at, as a part of a high school work experience course, 3 students have been placed in 3 different burger restaurants. Day has been placed at Burger Shack, Shelly has been placed at Big's Burgers, and John has been placed at the Burger Haven. Detailed below are the first 2 orders taken by each student and the total cost calculated for each order. So if I look at Burger Shack for Dea, the first one she said was $28 for 4 burgers and 2 salads. For the second one, she said that it was $34 for 6 burgers and 1 salad. At Big's Burgers, Shelly said that it was $18 for 1 burger and 3 salads, and that it was $54 for 3 burgers and 9 salads. And lastly, at Burger Haven, John said it was $32 for 2 burgers and 4 salads, or that it was $42 for 3 burgers and 6 salads. If we said that X dollars is the cost of a burger, and that Y dollars is the cost of a salad, then we can write 3 different systems that are going to match with the information we have here. So first, we're going to pull from the first sentence and then say that for Dea's, it's going to be 4x or 4 burgers plus 2y or 2 salads is going to equal $28. And that 6x plus y is equal to $34. For Shelly, we have x plus 3y is equal to $18. And we have 3x plus 9y is equal to $54. And for John, 2x plus 4y is equal to $32. And 3x plus 6y is equal to $42. Now, if I'm just looking at the first case, if I'm looking at Dea's Burger Shack, we can write the equations in terms of y and then graph it into our graphing calculator to find where they intersect. So I'm going to take my first equation and I'm going to say if 4x plus 2y is equal to 28, then 2y is going to equal negative 4x plus 28, or y is going to equal negative 2x plus 14. I'm going to call that y1. For the second equation, I'm going to state that, well, if 6x plus y is equal to 34, then y is going to equal negative 6x plus 34, and I'm going to call that y2. And then I'm going to go ahead and graph out these on my calculator. I'm probably going to have to change my window settings so that I can see both the intercepts, and I don't need to go too far into the negatives because obviously both values are going to be positive in this case. So I'm going to graph out my equations. I'm going to get, that's going to be my approximate one for y2, and I'm going to get that this is going to be my approximate one for y1. And oops, when I solve for where they intersect here, I'm going to see that they intersect at the point of 5 and 4, which means that given this situation, a burger is $5 and a salad is $4. When I move on to Big's Burgers, then I'm going to do the same process, and I'm going to state, well, if x plus 3y is equal to 18, then 3y is going to equal negative x plus 18, or y is going to equal negative 1 over 3x plus 6. And I can call that y1. When I'm doing the second equation, well, if 3x plus 9y is equal to 54, then 9y is going to equal negative 3x plus 54. And when I divide everything by 9, y is going to equal negative 1 over 3x plus 6. And I'm going to call that y2. I graph them out on my calculator. Well, I'm going to have y1 is going to look like this, and y2 is going to look like this. And then I see that they're equivalent equations. So can I determine the cost of a burger and a salad? In this case, the answer is no. They have no clear solution because they are equivalent equations. So I can see that right away one of the criteria is I need two different equations for them to ever have the chance of crossing. What about in the last case? Well, I'm going to have 2x plus 4y is equal to 32, which means that 4y is going to equal negative 2x plus 32, or y is going to equal negative 1 over 2 x plus 8. I have my second equation, and I can say that if 3x plus 6y is equal to 42, 6y is going to equal negative 3x plus 42, or y is going to equal negative 1 over 2x plus 7. There's my y2. There's my y1. And when I graph them out, I see that I have y1 is going to look like this. And y2 is going to look like this. And when it asks, how do I know that an error has been made? Well, I have two parallel lines, which means that in this case, there is no possible solution. The lines will never cross. Now, how does this differentiate from example C? Well, in example C, even though she put the order in twice, the numbers would still match up for both of those, so it just means that we don't have enough information. We need a different equation for this to work. For example, D, he did have two different equations, but he charged different amounts for every single possibility for the two equations, which means that he probably put one of the values in incorrectly. So in this case, there is no solution. So when I'm stating the number of solutions that any given problem can have, in all the examples, each system of equations had, or in the first lesson, they all had one unique solution, which means that it always had one point where they crossed and would always work. But as we've seen in the last page, they can either have no solution, one solution, or an infinite number of solutions. That would be like example C. Because in example C, there were two of the same line, so any point on that line would work, so there was an infinite number of possibilities. We didn't have enough information to prove that one would be different. So, if I'm graphing each of the systems and stating the number of solutions that exist for each of these, well, I can graph the first one, and I'm going to have my equation 1 is going to look like this. My equation 2 is going to look something like this. And in this case, I'm going to have one solution. Crosses once, will never touch again. In the second case, I have equation 1 is going to look like this. Equation 2 is going to look like this. And because there are two parallel lines, there is no solution. In the last case, I'm going to have equation 1 is going to look like this. I should probably move that over just a little bit. That's all right. For equation 2, I need to isolate y, so I'm going to say that negative 2y is going to equal negative 6x plus 4, or that y is going to equal 3x minus 2. And because when I change them around, they are the same equation, equation 1 and equation 2 are equivalent, this one has what we call infinitely many solutions. So any point that exists on this line that's going to go on forever and ever and ever is a possible solution. If I'm completing the following chart, then I have a few possibilities. I can say that for the number of solutions, well, either I can have one solution, I can have no solution, or I can have infinitely many. For one solution, I just need to have two lines that are going to cross once. For no solution, I just need to have two parallel lines. And for infinitely many, I'm going to say that there are two overlapping lines, which we call coincident. Coincident is a way of saying that they overlap each other. What are the requirements for this? Well, in order for it to have only one solution, the only requirement is it needs to have different slopes. Doesn't matter what the slopes are, if it has different slopes, it's going to cross once, never touch again. For no solution, they have equal slopes but different intercepts. For infinitely many solutions, they have to have the same slope and same intercepts, which means that they are equivalent equations.